Okay, so we're still on the 2010 Optics and Waves paper, and this is question 2. This is level 2 physics, by the way. A. Ashley places a pin in front of a concave lens. Concave lens, highlighted, bolded for us. The focal length of the lens is 15 centimeters, so that's F. The pin is 20 centimeters from the lens, so that is our distance to the object. Calculate the distance from the image to the pin, of the pin to the lens. So this is DI that we're looking for, and straight away, if you've identified these factors, these variables, FDO and DI is the one you're looking for, you'll know that you need to use Descartes' formula 1 over F equals 1 over DI plus 1 over DO. And let's see, we just plug all the numbers in. Basically it's a concave lens. Maybe it's a good idea to do a quick sketch. There's our concave lens, here's our axes, very roughly, and we've been told the focal length is 15 and the object is placed outside that. So very roughly speaking, parallel light ray reflects through the focal point, and one going So we don't have a virtual focus. The focus is a real focus, so it's going to be a positive number, and in fact everything's going to be positive because they cross over here. Our image we would expect is over here, and it could be closer or further apart, further away than the object, but I don't know for certain until I plug it in this calculation or draw a proper scale diagram. This is just a rough sketch. If you know your ray diagrams well enough, you will know what the answer is. But anyway, moving on. In actual fact, it is going to be smaller. But anyway, all closer. But let's go ahead and do this. What are we looking for? We're looking for DI. So we can either plug the numbers in and then rearrange, or we can rearrange and then plug the numbers in. Just for this purpose, I'm going to plug the numbers in and then rearrange because it's just a little bit nicer in this case. So 1 over 15 equals, we don't know DI, 1 over DI plus 1 over DO, which was 20 centimeters. And we're sticking with the same units all the way through here. If I put these in meters, so it was 0.15 and 0.20, that would mess up my fractions because you've got a decimal and a fraction. So I'd have to, if I was going to stick with those SI units, I'd have to change the denominator to keep the ratios the same, lowest common denominator, but in this case should actually be going up rather than decreasing the denominator. But anyway, where do we go from here? I'm turning a relatively simple one into a relatively complex one, so let's 1 over DI equals 1 over 15 minus 1 over 20. So now what have I done here? Let me just, oh wait, I know I've done something wrong here, and you've probably worked it out if you're clever as well. This is a lens, but I'm dealing with a mirror, so let's just scratch that. Most of what I've said applies, but this time it's a concave lens, so it's like this, and that creates a bit more of a tricky situation. We've got a focal length on either side, and this time we'll have the light ray that goes through the focal length will, hang on, I'll stick with what I know. Parallel light rays will spread out as though they come from the focal length. Any ray that goes right through the centre, the optical centre, will just carry on straight through. So we can tell that this is where our image is going to be, and also what this means is this is our focal point here. It's a negative focal point, it's a virtual focal point, so that's going to change, and that's also going to change, and that's going to significantly affect our result. Otherwise I think we'd end up with something quite large. But anyway, moving through, 1 over minus 15 minus 1 over 20, so you're making that number smaller by a small fraction. You end up with DI, if you have to work out what that equals, just plug it into your calculator. It'll equal 1 over about 8 or 9. and then you take the inverse to get di, so you'll get di equaling, let's see, exactly on the marking schedule is 8.6 centimeters, or negative 8.6 in actual fact, because it's a virtual image. That image there is virtual, it's not real. Okay. B. Ashley then places the pin in front of a concave mirror. Okay, so now we're back where I thought we were, as shown in the diagram. Draw appropriate rays on the diagram to locate the image of the pin. So C is going to be the centre of curvature, F is a focal point. We're going to draw a parallel light ray that reflects through the focal point, and we're going to draw a light ray going through the focal point that reflects parallel, and that gives us our image. We should use a ruler where possible. Okay. Let's see. We don't have to give the nature of the image, but just out of interest it is. It's a real image. It's inverted, and it's diminished. That is, it's smaller. Okay. And then C. The height of the pin is 4 centimeters. The pin is placed at a distance of 12.5 centimeters from the mirror. Focal length of the mirror is 3.6 centimeters. So we've got another calculation to do here, but this time we're given the height of the object, the height of the pin, which is, it's meant to be an O, and I still can't draw an O. Height of the object, 4.0 centimeters. The pin is placed a distance, so DO equals 12.5 centimeters. The focal length of the mirror is 3.6 centimeters. Now, all of these, because we're dealing with this, the image and object and setup here, they're all real values, so we don't need to worry about negatives and so forth. So anyway, calculate the height of the image. So we're after HI. And the easiest way to do this is to find the magnification, I think, because remember the magnification is the height of the image over the height of the object, or distance of the image over distance of the object. And one way to do that is to use Descartes' formula, because we've got DO and we only need DI. So we can go 1 over F equals 1 over DI plus 1 over DO. I'm not actually going to calculate this for you, but I'll just show you how you do it. So F we know because it's 3.6 centimeters. DO we know because it's 12.5 centimeters. We plug those numbers in, rearrange to find DI. Once we've got DI, we just throw it in there, and then we use our DO again, throw it in there. We've now got the magnification. Okay, and that will work out to be about 0.4. It's definitely smaller, it should be less than 1, because of our diagram above we can see that the image here is definitely smaller than the object here. So anyway, carry on. Once we've got the magnification, we can then, that same ratio will be height of the image over the height of the object. We know the height of the object is 4 centimeters, so we plug that in, rearrange for the height of the image, and then we're all there, and you'll get something like 1.6 centimeters. Okay, if you didn't follow that, go back through and watch again, and keep watching through to replay it until you've got it sussed. D. Ashley then places the pin between the focal point and the mirror. So with the same setup, let's just sketch this out so that we know what we're dealing with. It is a mirror, so I'm dealing with the right ray diagram. Focal point's here, now she's got the pin between the focal point and the mirror, so that's where our object is. Discuss the reason for the nature, real or virtual, and position of the image formed under these conditions. So we need to know, first of all, and we're going to use this ray diagram to work out what the position is, and from that we'll work out the nature, and then we can discuss the reason for those. So here we go. There's our first ray reflecting parallel ray, reflecting through the focal point, and then we can have, because we're inside the focal point, it's a little bit hard to use that in this case, but we can use the equal angle law. So so this angle, let's do that in a different color so it's very obvious. This angle here is equal to this angle here, and that gives us the reflected ray. And you can see that they're spreading out, so that means they would appear to come from a point, oops, I hit a button, hopefully it's, yep, there we go, still out. They appear to come from a point here, so there's your image. And So the reason for the nature, and it's asking specifically real or virtual, it's definitely virtual. It's also upright and magnified, but we're only interested in the virtual part. And the position. So it's on the virtual side, or it's a virtual image, because the light rays are spreading out over here, which means they appear to come from a point over here. So there's no actual real light rays coming from there, but when they reflect from the mirror over here, when they reflect at that point and this point, they appear to be coming, as they're spreading out, they appear to be coming from there. Okay. Yeah, I guess that's pretty much it. Another way of looking at it, I guess, rather than they appear to come from a point, is you could say they appear to meet at that point behind the mirror too. In this question, I think it's essential to have a diagram, and then you can just note down those kind of ideas about its virtual. So I think part of the question is correctly identifying whether it's real or virtual. So you can say it's virtual because the light rays appear to come from a point. You should use a diagram to show, I guess. Or you could say they're diverging. They appear to come from a point because they're diverging upon reflection. There we go, that's the end of that question.